Hello, welcome to the section Graph Algorithms. In this section you'll get a taste of functional algorithms. List prepending will be one dominating theme here. We'll start by looking at list reversal and how prepending helps in dealing with algorithms. We'll then look at an efficient algorithm for list reversal using list prepending. We'll implement functional topological sorting and improve it to handle digraphs with cycles. By the end of this section, you'll have seen some design principles for a functional algorithm design. Now we move on to the first video of this section that deals with reversing a list. In this video, we'll learn to share node among multiple versions. Graphs are a very important data structure. They're used to model related entities. A type of graph widely used are directed graphs, also known as digraphs. We'll implement functional versions of common digraph algorithms. For example, traversing a graph and visiting each node to do something useful. Topological sorting is a digraph algorithm used to compute nodes' order of precedence. Build tools, such as make, need to order tasks based on precedence. Topological sorting is the algorithm used by such tools to process a task's dependencies before the actual task is processed. Now let's begin with reversing a list. Throughout the course, we'll be using Scala version 2.11.7. Let me show you our first implementation. We first define slow reverse method for integer list. Next, we write the case clause. And this is how the list is putted up, as per the algorithm we defined. Now let's give the values for the list. Slow reverse, and say the list contains 1, 2, and 3. And we have the list of integers in the reversed order. This is not a very efficient algorithm. We end up doing too much copying. This diagram shows the copying of nodes for a list with 3 elements. As we know, every time we append an element, we need to copy the entire source list. We cannot resort to pointer juggling, as in-place update is not allowed. Never forget that we work with immutable and persistent data structures. An append operation has big O of n complexity. As there are n appends, the total complexity is big N of n square. This version is not tail recursive and hence is prone to stack overflow errors. Let's try another version for reversing the list. First, we import Scala annotation tailRec. Now we use trail recursive and define the reverse list. As we did previously, we define the case. This algorithm returns the reverse list, as you can see. Now, let's give the input values to the list as 1, 2, and 3. The complexity of this method is clearly big O of n. Instead of copying nodes, we share them among multiple versions of the list. Here's the diagram which shows this algorithm in action. Maximizing sharing and minimizing copying are fundamental techniques when we design list-based functional algorithms. I'm sure now it must be clear to you what you should focus while designing such algorithms. In this video, we've learned different approaches to reverse a list. In the next video, we'll look at some more list-based algorithms and see these techniques in action.